In the vast reaches of our solar system, Jupiter reigns supreme as a gigantic mystery, captivating scientists and astronomers for centuries. Just when we think we understand the gas giant, this celestial behemoth shatters our assumptions. With its blend of unpredictable and often hostile behavior, mesmerizing storms with winds up to 640 kilometers per hour, and the enshrouded mysteries of concealed metallic oceans within its core, Jupiter still leaves scientists puzzled. Join us on an extraordinary journey as we delve into the depths of this enigmatic world, uncovering its secrets. Decades of extensive studies have demonstrated just how remarkably intricate Jupiter is. Just recently, 12 more moons orbiting the gas giant have been discovered. The total number of satellites around Jupiter is now 92, more than any other planet in the solar system. The latest moons discovered have sizes ranging from 1 to 3.2 kilometers. A majority of these moons have extensive orbits, with 9 out of 12 taking over 550 days to complete one revolution around the planet. Scientists believe that because these distant moons move in the opposite direction of Jupiter's rotation, they could be captured asteroids. It's been widely believed that Jupiter acts as a protective shield, safeguarding our planet from threats from outer space. In the past, astronomers have even suggested that this was one of the reasons life got a chance at evolving on Earth. But recent findings cast doubt on Jupiter's role as Earth's celestial guardian. Long-period comets, which originate from the distant regions of the solar system and take millennia to orbit the Sun, typically enter our vicinity. However, thanks to Jupiter's gravitational influence, most of these swiftly moving icy objects are flung away from the solar system before approaching Earth. So the chances of long-period comets colliding with our planet are extremely rare, occurring over millions or even tens of millions of years, and Jupiter's presence plays a crucial role in shielding Earth from these potential impacts. However, the gas giant's gravitational forces have both positive and negative implications for life on Earth. On one hand, its immense gravity prevents nearby space rocks from accumulating and forming into a planet. This led to the formation of the asteroid belt, a collection of numerous small debris fragments scattered between Mars and Jupiter. But nowadays, the gas giant's gravitational pull continues to influence asteroids, causing some to deviate towards the Sun. This change in their trajectory increases the odds of collisions with Earth, and we've already witnessed it in the past. In 1770, Lexell's comet passed just about 1 million miles away from our planet, an extraordinary proximity on an astronomical scale. Scientists believe that this comet had initially come from the outer reaches of the solar system and had a close encounter with Jupiter that redirected its path towards Earth. After completing 2 orbits around the Sun, the comet returned to a point of close proximity to Jupiter 9 years later, which subsequently ejected it from our solar system. The Jupiter shield theory, supported by previous computer simulations, suggested that the gas giant ejects countless long-period comets out of the solar system. And this theory even predicted the comet Shoemaker-Levy 9 striking the 5th planet in 1994. But computing resources weren't as powerful as they are nowadays, and scientists had to make a lot of calculations. Today, we have data that includes a greater number of short-period comets and near-Earth asteroids that intersect with Earth's orbit compared to long-period comets, and new simulations demonstrate a different picture. Jupiter's influential gravity interacts with the asteroid belt, causing gravitational resonances that clear out rogue asteroids and redirect them inward. Collisions between asteroids can also contribute to this process by dispersing rocky fragments into resonant zones. The inner edge of the asteroid belt is particularly affected by a phenomenon known as secular resonance, which drives material into the inner solar system. Jupiter's current mass allows it to both redirect comets towards Earth, as seen with Lexell's comet, and effectively remove them from the solar system. If Jupiter had only 1/5 of its current mass, it would still destabilize comets, but lose the ability to remove many of them. leading to a higher impact rate on Earth. The frequency of impacts plays a crucial role in the long-term evolution of life on a planet. Earth's geological record indicates that an impact rate of one major collision every 100 million years provides enough time for the biosphere to recover and thrive. However, a higher impact rate, occurring every few million years, could devastate the planet, hindering the development of a new biosphere. Some scientists believe collisions with Earth is also how water was brought here. But what about water on Jupiter? Water vapor was first detected on Jupiter in 1995. This discovery was made by the Galileo spacecraft, which conducted extensive observations and measurements of the planet and its moons. The onboard instruments of the Galileo spacecraft, particularly the near-infrared mapping spectrometer, detected the presence of water vapor in the planet's atmosphere during its close flyby. But recent data demonstrates water makes up approximately 0.25% of Jupiter's atmosphere above the planet's equator. While this may not sound like a lot, it's actually an immense amount of water. Jupiter, probably the first planet to form in our solar system, contains a significant amount of gas and dust that didn't become part of the Sun. Knowing just how much water is locked up in Jupiter is crucial for scientists studying the formation of the solar system. In recent years, a team of researchers used telescope data to discover a substantial presence of water within Jupiter's famous Great Red Spot. Launched by NASA in 2012, the Juno spacecraft currently orbits the gas giant, taking close-up pictures of its clouds. Equipped with advanced instruments, the spacecraft has now revealed even more evidence of water on Jupiter. Because this massive gas giant holds more than double the combined mass of all the other planets in our solar system, even small fractions of water on such a massive planet would amount to a significant quantity, far exceeding the amount of water found on Earth. Water in the gas giant's atmosphere is also the reason why Jupiter, just like Earth, has its own mesmerizing displays of lightning 100 times brighter than terrestrial lightning and peculiar hailstones. Lightning has been detected in the planet's water clouds in the past, where water droplets collide with electrically charged ice crystals. But the Juno spacecraft has also spotted dim lightning at higher altitudes in the atmosphere, where the temperatures drop to approximately minus 87 degrees Celsius, too frigid for water to exist in its liquid state. So how does lightning happen under such conditions? The answer to the mystery lies in ammonia, a remarkable component in Jupiter's atmosphere that serves as a natural antifreeze. In the upper atmosphere, water ice crystals combine with ammonia vapors and melt. These water-ammonia droplets then collide with additional ice crystals from below, creating an electrical charge that generates lightning. Below the ammonia ice clouds, the ammonia water droplets undergo continuous growth until they become too heavy to remain suspended in the air and resemble large hailstones like we have on Earth. Scientists believe that these mushball-like objects descend deeper into Jupiter's atmosphere. But now, let's travel even deeper into Jupiter's innermost layers. Previously, it was believed that our solar system's giant worlds all have a rocky core. This was the accepted theory for a very long time, but recently, scientists have started to doubt this theory. Using Juno's orbit data, scientists are still studying how matter is distributed inside Jupiter, and recent discoveries have unveiled an unexpected mystery lurking within the gas giant's core. Jupiter's core has extremely high pressures, much greater than on Earth, and temperatures as hot as 20,000 degrees Celsius. To understand these conditions, scientists use powerful lasers to compress samples and mimic the planet's pressures in a laboratory. The Center for Matter of Atomic Pressures at the University of Rochester is at the forefront of this research. The density of materials in Jupiter's core depends on their composition and physical properties. And just recently, scientists have discovered that Jupiter's core is not as compact as they thought it was. Deep within its inner regions, only 18% of the material is rocky. Jupiter is predominantly made up of hydrogen, accounting for about 90% of its composition, along with roughly 10% helium and trace amounts of other elements. In the outer layers of this gas giant, hydrogen exists as a colorless and transparent gas, in the same form as it exists here on our planet. As you descend deeper into Jupiter, the increasing atmospheric pressure transforms hydrogen into a bizarre, dense fluid that conducts like a metal. So what is this substance? Approximately 10% of the way towards Jupiter's core, along its radius, the immense volume of hydrogen gas that forms the planet's atmosphere becomes compressed into a unique form known as liquid metal hydrogen. Liquid metallic hydrogen possesses properties similar to water, with low viscosity, excellent electrical conductivity, and efficient thermal conduction. Within Jupiter, this abundant substance transforms the planet into one huge generator. On Earth, elements exist as solids, liquids, or gases, depending on temperature and pressure. While hydrogen is typically a gas on our planet, it can be compressed and cooled artificially to become a liquid or solid. However, even in these states, hydrogen retains its non-metallic nature, poorly conducting heat and electricity. In contrast, metals excel at conducting heat and electricity due to their atom arrangement. Deep within the gas giant of our solar system, hydrogen undergoes extreme temperature and pressure, which allows for peculiar states including liquid metallic hydrogen. Hydrogen atoms under these conditions shed their electrons, resulting in a mix of free-floating hydrogen nuclei and electrons. This electron mobility resembles metal behavior. There's a theory that Jupiter's core might be filled with vast oceans of this substance, and based on previous estimations of the Jovian core's mass, it could be 12 to 45 times more massive than our planet. A 40,000-kilometer deep layer of liquid metallic hydrogen, combined with Jupiter's rapid rotation of about 10 hours, generates a colossal magnetic field that spans an astonishing distance of 725 million kilometers. This magnetic field stands as the largest in our solar system, and it contains mysteries of its own. Exploring regions more than 320 kilometers down into Jupiter's atmosphere, scientists have identified a newfound area known as the Great Blue Spot, not to be confused with Jupiter's Great Red Eye Storm. Researchers knew that the Jovian magnetic field was complex, but they had no idea just how weird it was. And it has something to do with the Great Blue Spot. The Jovian magnetic field is 20,000 times stronger than the Earth's magnetic field. But now, scientists have discovered that its strength is volatile. Unlike the Earth's dipolar magnetic field, the gas giant's magnetic field originates from a wide area in the northern hemisphere and re-enters near the South Pole. Researchers have also identified a concentrated region just south of the equator, the Great Blue Spot. Is like a second Jovian South Pole located near the equator. The colossal storm that's raged for centuries is probably caused by the presence of high concentrations of ammonia in the atmosphere. The intensity of the magnetic fields in the Great Blue Spot undergoes fluctuations of up to 1% per year, strengthening and weakening across different regions. By the end of the extended Juno mission in 2025, scientists will have ample evidence to evaluate their hypothesis. As research continues, we're going to encounter new mysteries about the gas giant. Since the Great Blue Spot and the Great Red Spot are located at the same latitude, it's possible the two phenomena are somehow connected. Gas giants are typically characterized by their high temperatures, especially in their upper atmospheres. In our solar system, there are two such giants, Saturn and Jupiter. However, Jupiter doesn't have a consistently high temperature throughout its entire structure. The solar system's largest planet is mostly known for its massive storm, twice the size of Earth, the Great Red Spot. But the gas giant has other spots too. The Great Cold Spot is nearly as large, and scientists have been observing this phenomenon for years now. At its largest, the spot is approximately 12,000 by 24,000 kilometers across. But unlike the famous red spot, this intriguing atmospheric feature stands out as a region of significantly colder temperatures compared to its surroundings, about 200 degrees cooler than the surrounding atmosphere. The Great Cold Spot is volatile. disappearing and reappearing from time to time. Scientists have discovered that this phenomenon's recurrence is triggered by the planet's auroras. Because of this correlation, the spot's age is about the same as the age of Jupiter's polar lights, which is in thousands of years. Jupiter's auroras, similar to Earth's, are produced by charged particles interacting with the planet's atmosphere near the poles. However, the gas giant's polar lights are more stable and intense as they receive particles from both its moons and the Sun. New findings indicate that these auroras transfer energy to Jupiter's atmosphere, creating a temperature difference between the upper and lower regions. This temperature contrast leads to the formation of a swirling vortex, resulting in a cooler patch that is distinct from the aurora and its surroundings. Earth also experiences similar effects. However, the combination of factors like Jupiter's rotation that helps retain heat in specific areas and the varying nature of these events makes the occurrence of polar lights on our planet less consistent. Another discovery made about the gas giant was that, contrary to common belief, Jupiter doesn't actually orbit the Sun. The center of gravity between Jupiter and the Sun does not reside within the Sun itself, but instead exists at a specific point just above the Sun's surface. In space, where a smaller object seemingly orbits a larger one, both objects actually orbit around a combined center of gravity. Consider Earth and the Sun, for instance. In this case, the center of gravity is so close to the center of the larger object that its impact is hardly noticeable. The larger object appears motionless, while the smaller object traces a seemingly perfect circular path around it. The same happens when the International Space Station orbits the Earth. Both the Earth and the ISS orbit around their shared center of gravity, even though our planet seems to be completely stationary, while the ISS appears to orbit the Earth in perfect circles. This principle generally holds true for most planets in our solar system. Even Saturn has negligible influence on the Sun's position in space. However, as the difference in mass between the two objects decreases, everything changes. In the case of Jupiter, its immense size causes the center of mass, known as the barycenter, to exist 1.07 solar radii away from the Sun's center, approximately 7% of a solar radius above the Sun's surface. This means that both the Sun and Jupiter orbit around this particular point in space. As the voyage of discovery continues, the enigmatic depths of Jupiter hold even more surprises yet to be unveiled. Stay tuned here to be the first to witness cosmic newfound wonders, and thanks for watching.